And the synchronization problem that we will be discussing today is going to be the dining philosopher's problem. So last time I gave a high-level description of the dining philosopher's problem. And to just refresh your memory, in this problem we have a number of philosophers, in this case 5, sitting at the dining table, and each one has his own plate, but they are sharing chopsticks. So this chopstick is shared between this philosopher and this philosopher. And a philosopher can eat only if both chopsticks are in it. So let me draw it here. So maybe I need a. So this is, let's say, 0, 1, 2, 3, and 4. So this is philosopher 0, philosopher 1, philosopher 2, philosopher 3, philosopher 4. And the chopsticks, this is chopstick 0, chopstick 1, chopstick 2, chopstick 3, and chopstick 4. Now, philosopher 0 needs chopsticks 0 and 1. Philosopher 1 needs chopsticks 1 and 2. So in general, philosopher I needs chopsticks I and what? And I plus 1. So chopstick, philosopher 0 needs chopsticks 0 and 1. So I and I plus 1. But what about philosopher 4? Philosopher 4 needs chopsticks 4 and 0. So we need to do the add here in a circular manner. We need to do the mod. So it's going to be, this is going to be I plus 1 mod what? Mod, how many do we have? We have 5. So it's going to be mod 5. Okay, so each philosopher needs chopstick I and chopstick I plus 1 mod 5. And so the first solution that we will look at is a straightforward solution where we have a semaphore for protecting each chopstick. So we have an array of semaphores in which there is one entry, one semaphore for each chopstick. And each philosopher must check both semaphores before they can eat. So we have each philosopher is going to check on semaphore I or chopstick I, then he's going to check on chopstick I plus 1 mod 5. Then he's going to eat. Then he's going to release both of them. Release both chopsticks. Okay? Now, the problem with this, so this is a reasonable solution. But the problem here is that this may cause a deadlock. So can you give me a specific scenario that will cause a deadlock? So when we say a scenario, I mean a sequence of events.
If each philosopher gets one chopstick?
Yeah, if each philosopher gets one chopstick and is waiting for the other, then we will have a deadlock. But how will this happen? How will each philosopher end up with one chopstick? Can you give me more details about how this will possibly happen?
If they get one and then they get interrupted, and then the next one gets one,
Yeah.
then
Yeah.
it gets interrupted.
Yeah, exactly. So if philosopher 0 gets 0, then loses the CPU. And philosopher 1 gets chopstick 1, then loses the CPU. Philosopher 2 gets 2 then loses the CPU, philosopher 3 gets 3 then loses the CPU, and 4 gets 4 and loses the CPU. So in that case, each one of them will be holding one semaphore, one chopstick, and waiting for the other, but the other will not get released because, say, philosopher 0 is going to be holding this, philosopher 0 is going to be holding this chopstick, but this chopstick will be held by philosopher 1. And philosopher 1 is waiting because he's waiting for this. Same for philosopher 2, he's waiting for this, and 4 is waiting for this, and each one of them is waiting for a chopstick that is held by another philosopher. So now this, in this case, a deadlock is possible. But the question is a deadlock likely? So there is a difference, between possibility and likelihood. How likely is this scenario to happen?
Very unlikely.
Why?
Because you're counting on it. You're counting on each process losing the CPU at almost the exact identical spot in the program.
Yeah.
So it gets one. It gets one chopstick, and then before it can get to the second, it loses, and then you have to have the same thing for 0 to n-1.
Yes, yeah. They are unlikely to be trying to do the same thing at the same time. When we design a solution, usually we want a solution that is guaranteed to work correctly. So we don't rely on, chance, or we consider if a scenario, if a bad thing is possible, we just consider this an incorrect solution, or a solution that will have a deadlock. Okay. Even if it's possible but extremely unlikely, we still think of it as a bad solution, or a solution that may cause deadlocks. So we try to do it to play it safe. We want a solution that is guaranteed not to have any deadlock. Now, if we want to guarantee not having a deadlock, there are multiple ways of doing this. One way of doing this is allowing only 4 philosophers to be sitting at the table. So if we say that this guy is not sitting at the table, you will never have a deadlock, because now you will have 4 philosophers competing for 5 chopsticks, 5 resources. So you are decreasing the number of processes that are competing, and the number of resources is still the same. So now this scenario will not happen, because 0 will get this, 1 will get this, 2 will get this, 3 will get this, but there is no number 4, so this will not get reserved. And number 3, when it gets 3, it will eventually get number 4. There will be no deadlock. So with 4 philosophers and 5 chopsticks, a deadlock will not happen. Now, another way, well, this is basically, here we are limiting the number of resources, or limiting the amount of parallelism. So it's not a good solution, or basically changing the problem. Basically we're changing the problem from a 5 philosopher problem to a 4 philosopher problem, and making it an easier problem. There are other solutions with 5 philosophers. We can still keep 5 philosophers and solve this problem. One solution is to put these 2 lines, or 2 weights, in a critical section. So introduce yet another semaphore, another mutex semaphore that will protect these 2 lines. So you wait on mutex here, and then you post or signal mutex here. This way, you are guaranteed that a process will not get interrupted here. And again, when we say it will not get interrupted, we do not mean that it will not lose the CPU. Right? What do we mean by it will not get interrupted? When we say not getting interrupted in this context, we don't mean that it will not lose the CPU. It may lose the CPU, but
It won't let another process execute that critical section.
yeah, exactly. Yeah. So the system will not let another process access the same critical section, a critical section that is protected by the same semaphore. So if we introduce a semaphore here that we call X, then any other process or thread that is trying to access a section protected by X will be blocked. So this is what we mean by not getting interrupted. So you are never guaranteed not to lose the CPU. Okay, so this is one solution. Another solution is an asymmetric solution. So, which means that we can have processes pick their semaphores in a different order. So if we can say that an even numbered process gets the right chopstick before the left, and an odd numbered process gets the left before the right. So even gets left, or let's say right before left, and odd gets left before right. According to this scheme, 0 will get, 0 is even, so it's going to get the right before the left, so it's going to get 0. Now let's assume that, we'll have this, the philosophers getting hungry in order, 0, 1, 2, 3, 4. Then 1, so now 0 will get this. Then even if 0 gets interrupted, 1 will not be attempting to, philosopher 1 will not be attempting to get this chopstick. It will get the left before the right. So it will be getting this first. Then let's say 1 gets interrupted. Then 2 will be attempting to get right before left. So 2 will be attempting to get this. Now it will not get this, so it will be waiting. Then 3, which is odd, will be trying to get left before right. So it will be trying to get this, 4. And it will get 4. Okay. Then 4 will not get anything. Both will be taken. So then now when 0 gets the CPU again, it will be able to get this. When 0 gets the CPU again, it will get this. This will become will be available for 0. And when for process number 1, so 0 will eventually get this. Now, process number 1 will have this available, but it will not have this available. So if you think about this solution, it will be impossible for one process to be holding one chopstick and waiting for the other, because of these waiting processes. So basically, you can think of these waiting processes here like processes that are no longer or temporarily not competing for the chopsticks.